Hello, we are the Miniature Smart Car Hardware Design Team. My name is May, I'm an undergraduate at Rutgers.
I'm Michael, undergrad at Rutgers. And I'm Brandon, also an undergrad at Rutgers. Cool. All right, well, as it's loading, so as you guys know, at WINLAB there's a lot of car projects, so like self-driving cars and AI projects. And in the past, these projects have used remote control and smart car kits, like these ones over here on the top right. However, these kits have a lot of shortcomings. And so our goal is to design a 1/15 scale model of a car that tries to address some of these problems. So designing it from scratch, some of the main things that we want to include, there's three main design goals that we want to accomplish. The first one is to have the 1/15 scale and like to fit in the orbit smart city, which is behind you guys over there. The second goal is to adhere more closely to the mechanisms of a real car, and I'll go more into detail about those next. And then the last one is to include sensors, so that way we can calculate our position and create a feedback loop that allows us to control the device more accurately. And so here are some pictures of our car, and we have it on the table here too. So some of the design principles in a real car that we hope to achieve are so the first one is having to do with this with how the car turns. So on the left, you have a diagram of the car making a right turn, and as you can see, one of the complications with this is that the outer side or the outer wheel has to turn more than the inner wheel because the arc has a larger radius. And so to accomplish this, you have to use something called a differential gearing system. And so here we have our CAD designs. On the left is the differential gearing system. And so it allows one motor to drive the two different back wheels at different speeds. And then on the top right, we have another complication with steering. And so since the radius of the two arcs on the left and right side of the car are different, one of the wheels has to actually turn more than the other one for them to converge on a single turning point. And so here we have a design of an Ackerman steering linkage, which allows you to, which has a property that the inner side will turn more than the outer one. And so here's our final design. We used Fusion 360, which is a CAD software, computer-aided design, and we have a lot of like animations of the parts being assembled. So on the top left, we have like the bottom half assembly, which is like has the motor and the sensors and the differential gearing. The bottom left is like the steering mechanism, and the top middle we have an animation of like the drive system running, and you can see we have it set up in the design to run one side faster than the other, which demonstrates how the differential works. And then at the bottom we show the full assembly, and here's the final car.
So here's a high-level overview of our electronic system. I'd like to highlight two pieces of hardware specifically, the Intel upboard and the TNC microcontroller. The Intel upboard is a single board computer that essentially is the brain of the electronic system. It runs high-level processes such as self-driving algorithms and neural networks, but at slower computational times. Alternatively, the TNC microcontroller is responsible for lower-level processes. It ingests data real time by interfacing with signals, and that allows for real-time control of the car. A good example of this can be seen with the encoder. The encoder is a sensor apparatus that converts angular position to output signals. And then these signals are read by the TNC microcontroller, and then they can provide good data for odometry, such as speed, position, and velocity. So another important aspect of our electronic system is square wave signals. These signals are useful for controlling the speed of the car. So on the left-hand side here, you can see an oscilloscope, a device used to measure and analyze electronic waveforms. And here is displaying a square wave signal. The distance between either two on pulses or two off pulses is known as the period. And by varying the period, you can change the frequency at which the motor turns. So this process begins with the TNC microcontroller. It generates and sends signals to the stepper motor driver. which in turn converts these pulses into steps. So one pulse converts to one step. And this process is essentially used for speed control of the stepper motor.
So for the embedded software, we created a 3-component architecture, starting at the top with ROS node. ROS stands for Robot Operating System. It's basically an open source framework that allows you to reuse and develop code for robotic applications. And it sends down a desired car speed that you want, as well as a turning curvature, which is simply inverse of the turning radius. This is sent to the brain of our system, the upboard, which processes this and calculates the speed you want into rotations per minute at the back wheels, as well as the servo angle to steer the wheels. And then this is passed down to our microcontroller, which then converts these pretty fast because it's the lowest level to square wave control signals that control the stepper motor, which makes the car go faster or slower, and the servo motor, which controls the steering. But our microcontroller also takes in encoder signals from the back wheels. And this gives us picks, and using these picks, we can calculate how far the back wheels have linearly traveled. And from this, we calculate the position of the car over time along the arc, as well as angle. And then we send this back up to ROS that can store this information. And in the bottom left, you can see this creates a feedback loop where going top down, we send in control data where we want the car to go, how fast, and then back up to the ROS node, we send sensor data. And it creates this loop where you can create repeatability because you can continually adjust data and get feedback. And up here, this is some of the code we were able to prototype that displays the position of the car in Cartesian 2D coordinates, as well as the angle of the car along that arc. And for future work, one of the most important things would be to fix our electrical system because unfortunately, we did burn through our motor drivers. As you can see, we did start a small fire with our battery pack. Anyways, 3 projects that can be applied to this car could be implementing pure pursuit algorithms, which allow you to tell the car a bunch of points along a continuous path, and it tries to go to each point along some arc. Additionally, we hope to implement LiDAR sensor technology or real sense cameras, and hopefully we can start detecting things at distances, as well as with our encoder data, it creates more precise measurements. And finally, we hope to apply self-driving AI, such as convolutional neural networks, where we start back propagating data instead of just manually sending it. Any questions?
So thank you.
And we have the car here if anyone wants to check it out after.